Welcome back to Math 110, Introduction to Number Theory. And in this video, we're going to talk about Euler's criterion and the Legendre symbol. In the previous video, we got a taste of Euler's criterion, but it was underexplored in the form of testing whether a residue was an element of the set S1. So, let's start off by defining the Legendre symbol. For C and P integers, where P is an odd prime, then the Legendre symbol, C over P in parentheses 2, I'm never really sure how to say it, is defined to be 0 if C is 0 mod P, 1 if C is non-zero mod P and it's a quadratic residue mod P, so if C is a square mod P, and it's -1 if C is a quadratic non-residue mod P. And I should say that this notation, it's the one that I know that is maximally unambiguous, but the book's notation, or actually so commonly you'll also see it without the two, and also the textbook we're using uses C/B in parentheses. The parentheses are how you know it's not just division. Yeah, so this may seem like a strange definition, but at least we can see right off the bat that it tells us whether a number is a residue or not, and also whether it's 0. But this ends up enjoying a number of very useful properties, which we'll talk about in a moment. But first, some immediate facts. The first is that we can change the top of the Legendre symbol to another number that is congruent mod P, and that's just because whether a number is a residue or not is just a matter of what it's, it's an invariant under which element of the congruence class it is. Also, if we have a square, then it's 1. Oh, well, not quite. This should be if C is not congruent to 0 mod P. Because if C is 0, then the Legendre symbol is 0, even if you square 0. So let's look at some values of Legendre symbols, mod 7. So in this table, I have the different residues of C, and I also have C squared. And this is mainly just so that we know what the residues, the quadratic residues are. So we see that the non-zero quadratic residues are 1, 2, and 4. So C over P Legendre symbol. So when C is 0, it's 0. And then when C is 1, 2, or 4, it's positive 1. And otherwise, it's a non-residue. -1 is the Legendre symbol's value. So the reason why the Legendre symbol is defined in the way it is specifically so that this theorem holds, Euler's criterion. So here's the criterion. Let's say that C is any integer and P is an odd prime. Then C over P Legendre symbol is congruent to C to the power of P minus 1 over 2, mod P. So you should compare this to the C being in S1 test from the previous video. And so before, or in that video, just by the way, when C was in S1, then this was congruent to 1. And if it wasn't, then it's not congruent to 1. So in this, the new thing is that it's congruent to -1 if it's not congruent to 1 or 0. So case 1, we'll handle this one right off the bat, which is when C is 0 mod P. And then we can just compute both sides. 0 to the power of something is 0, and also 0 is a square. Or, well, no, 0 is 0. So it's 0. So case 2 is when C is non-zero mod P. So let's let G be a primitive root mod P so that we have something to analyze with. And let's let K be some natural number where C is that power of G, which we know exists because C is non-zero mod P. So recall that once we've put it into this power of a primitive root form, C is a quadratic residue if and only if that exponent k is even. And this was a consequence of Fermat's little theorem and also basic things about solving linear congruences. Okay, so let us calculate then what c to the p minus 1 over 2 is. So we substitute in g to the k, and then swap the exponents. And then this is a fact that we've mentioned, we've gone over a couple times. That's g to the power, a primitive root to half its order is minus 1. And that is just to recall because, well, g to the p minus 1 over 2 squared is congruent to g to the p minus 1, which is congruent to 1 because p minus, well, Fermat's little theorem. And x squared congruent to 1 mod p, when p is an odd prime, has exactly 2 solutions. And we can write them down. X is 1 or minus 1. So, first of all, we know that g to the p minus 1 over 2 can't be 1, because if it were 1, then p minus 1 over 2 would be a smaller order, or an exponent smaller than the order of g, and that's not good. So anyway, it has to be minus 1, and that's what it is. So anyway, so we've taken c to the p minus 1 over 2 and turned it into minus 1 to the k, and that's fairly easy to analyze. If k is even, it's 1, and if k is odd, it's minus 1. And, well, that matches up with this. So that's Euler's criterion. So let's use it to calculate some examples. So is 2 a quadratic residue mod 5? So we take 2 to the p minus 1 over 2. So 2 squared, which is 4, which is minus 1 mod 5. So it is a non-residue. And we can check, just let's square each of these numbers. So this is c and c squared. So 1, 0, 1, and 4. And that repeats backwards. So 1 and 4 and 0 are the quadratic residues. And 2 is not in that list. So we got minus 1 as expected. And 4, well, it's obviously a square. So this should be 1. But nevertheless, we calculate 4 squared, which is 16, which is 15 plus 1, which is 1 mod 5. So 4 is, according to Euler's criterion at least, a quadratic residue mod 5. And it's in the list. Okay, so the Legendre symbol is useful because it gives us these fancy other calculations that we can do. And also it's nice when you have notation so that you can manipulate it instead of it just being in words, you know. A is a quadratic residue mod p. That's a long thing. So we've got this tertiary notation. And one of the amazing things is that it's completely multiplicative. So whenever there's a product in the top, we can turn it into a product of Legendre symbols. So now that we have Euler's criterion, this is pretty straightforward. We take the Legendre symbol and note that it's congruent to, well, AB to the p minus 1 over 2 using Euler's criterion, and then use that the product to an exponential is the product of the exponentials, and those happen to be, by Euler's criterion, the Legendre symbols again. So there's one thing I did not mention here, which is that this is in minus 1, 0, 1, and this product is in minus 1, 0, 1. And since this is mod p and it's odd, since these are congruent, then they're equal, because there's an equality here. This This wouldn't work mod 2, for example, assuming the Legendre symbol were actually defined for 2. Also, the Legendre symbol is always 1 if we were to define it for 2. Because, everything's no, it's not always 1. It would be, if we were to define it, which we haven't, it'd be like 0, 2 would be 0, and 1, 2 would be 1. So it just takes the top mod 2. So here's an example using this property. So is 6 a quadratic residue? Mod 7? Well, we can take the product of the Legendre symbols for 2 and 3 and see. So this isn't like calculating it. I'm just verifying that it actually works. So 0, 1, 2, and 4 are quadratic residues mod 7. And so 2 gives us 1, 3 gives us minus 1 because it's not on the list, and also 6 is not on the list, that's minus 1, and great. It actually does work out. Yeah, strictly speaking, we don't need Euler's criterion to prove this property, though there's some parts of it that you don't need. But anyway, it's just very straightforward when you do have it. So a corollary, just to say what the logical conclusion is to that, is when you have an odd prime p and a non-zero integer, or let's just say a positive natural number, where we have a prime power factorization of it, then to compute the Legendre symbol for whether n is a quadratic residue mod p, we can turn it into a product of the powers of the Legendre symbols of each prime. So this question of what the value of the Legendre symbol is for a composite number does reduce to the problem of what is the value of Legendre symbols for every prime over a prime, odd prime over a prime. Oh, no, well, it might be 2, but so for primes over an odd prime. And something I forgot to mention is, where the previous lecture focused on actually computing square roots, what we're doing here is just inferring whether something has a square root at all, which is an easier problem as it turns out, due to a few things that, we have Euler's criterion, so it just happens to be easier. So anyway, so continuing on with inferring properties of existence of square roots. So here's an example. If you take a number and multiply it by 4, is it something with a square root? Well, I guess you should realize that if a square root of 4n is the same as, square root of 4n would be 2 square root of n, so it just reduces to whether n has a square root. But let's do partial prime power factorization and see. So 4n is, of course, 2 squared times n. So we've got the Legendre symbol 2 over p squared and times n over p. And I didn't need to square it. I just wanted to make it look more like the corollary. But anyway, this is going to, it's 1 or minus 1, but we're squaring it, so it's going to be 1. So it just is gone. I also forgot to say that the powers, since these symbols are all 1 or minus 1, because the primes are not going to, oh, it could be 0 too. Yeah, I should say if qi is not equal to p. So for each of the primes that are not p, we can reduce the, because the Legendre symbol is 1 or minus 1, we can reduce the power by mod 2. So, okay, so that was an example. Okay, now for our favorite recurring problem, which is minus 1 a number of the square root mod p. Here's a lemma. The Legendre symbol is 1 if p is 1 mod 4, and otherwise it's minus 1. So using Euler's criterion, we can calculate that the Legendre symbol is congruent. And actually it's equal to minus 1 to the power of p minus 1 over 2. And minus 1 to the power of something is easy to compute. But we can just look at the cases. So p, when it's 1 mod 4, when you subtract 1, that means 4 divides it. So that means when you divide by 2, 2 divides it. So that exponent is even. And in that case, we get 1. And if it's 3 mod 4, then we subtract 1. We get something that only 2 divides it, but 4 does not. We divide by 2, we get something that 2 does not divide. So it's an odd number, and we get minus 1. While preparing the lecture, I also realized that we could use Wilson's theorem to give another proof of this fact, using Legendre symbols, but not using Euler's criterion, but also using the fact that it's multiplicative, which we used Euler's criterion to prove it, but let's suppose that we did not. So, and in any case, this is just an exploration of what these different theorems can do. So is minus 1 a square mod p? Well, Wilson's theorem was that minus 1 is congruent to p minus 1 factorial. So that's a product, and we can write it as a product of Legendre symbols. And as we've discussed before, exactly half of the numbers 1 through p minus 1 have a square root, and the other half do not. So half evaluate to 1, the other half evaluate to minus 1. So p minus 1 over 2 is the number of them that evaluate to minus 1, and so we get this expression again. And then we continue with our analysis like before. Okay, so in a future video, we're going to talk about, one, how to actually compute whether 2 has a square root mod p, and it turns out to have a very simple condition. It's simply whether p mod 8 is 1 or 7. And if it's 3 or 5, then no, it does not have a square root. And that's important for the following reason, because we're also going to have this wonderful theorem called quadratic reciprocity. Quadratic reciprocity lets us take a Legendre symbol involving 2 odd primes and flip it over at the cost of just introducing a sign. And the way that the sign works is, so let's look at p mod 4 and q mod 4. And so the two options are 1 and 3, of course. And so if either of them is 1 mod 4, then this exponent ends up being even, and so the minus sign does not happen. And otherwise, if they're both 3 mod 4, the exponent ends up being odd, and so we get a minus 1. So this is explaining what this ends up being. Yeah, so that is not hard to compute. And once you flip it over, then you can reduce q mod p, and then factorize it, continue, flip things, maybe use the 2 rule here. And you can check whether something has a square root in that way if you wanted. So as an example, using these 2 theorems, so 6 and 7, or 6 is a square root, or does 6 have a square root mod 7? And I should say that this is the same as minus 1, 7, which is, as we've established, 7 minus 1 over 2, which is even, or wait, 3. That's minus 1 to the 3. So we should get minus 1 that way. But let's try it using these things that we have not proved yet. So we factorize it. And since 7 is 7 mod 7, 2 has a square root, and mod 7, and then 3 over 7. Well, since 3 is 3 mod 7, and 3 is 3 mod 4, and 7 is 3 mod 4, then they're both 3 mod 4, so we can flip it over at the cost of an additional minus sign. And then, okay, so then we've turned 6, 7 into 7 over 3. So 7 is 1 mod 3, and 1 definitely has a square root mod 3, so this evaluates to 1. And that minus sign gives us minus 1. So 6 does not have a square root mod 7. Okay, so that's it for this video, and I will see you next time.